welcome back to another video. This one we're going to talk about the concept of linear regression. Linear regression is a useful extension of what we talked about in our last lecture regarding scatterplots and correlation and association. So basically, linear regression is a process of calculating a line that best fits those data points that we got on a scatterplot. Hence, it's also called the line of best fit. So throughout this lecture, you're going to hear me use the term regression line, best fit line, line of best fit. All of those mean the same thing. All right, so I hope I don't confuse you guys with that switching of terminology, but they all mean the same thing. So what does the best fit line look like as far as equation-wise? Well, it's a line, so there's only so much it can do, right? So the line is, I have it here, y hat equals b naught, b sub 0, okay, I guess you can call it that, plus b1x. So first of all, why the hat? The hat is used because we can use this equation as a way of predicting the y value. What I mean by that is we use the data points to create this equation, and then we can use this equation to make predictions. It's just like hurricane forecasting, right? They put input data into a model, and then the output tells them where they think the hurricane's going to go, its direction. Very similar to what we're doing here. That's what all models do. So what are some of the attributes of this model? Some of the parameters. Well, B1 is the slope, right? And so essentially, guys, what we're doing is, from your algebra class, y equals mx plus b, that slope-intercept form. We're just doing that same thing, except for we like to put the intercept first. But the slope is b1. And so what does the slope tell you? Just like you learned in algebra. So the slope tells you how much the y variable will change if the x variable is increased by 1 unit. So if my slope is positive, it means that if I increase my x variable by 1 unit, my y value will go up by whatever the magnitude or the whatever the slope is. And then vice versa. If my slope is negative, an increase in the x direction will bring down my y value. Okay? And then b naught represents the y-intercept. We know that's the value of y when x is 0. Sometimes it makes sense in the context of our problems, and sometimes it doesn't. But the slope always should make sense in the context of our problem. Once we have a line of best fit, we are able to make predictions, as I said, by plugging in an x value. This is the reason for the hat on the y variable, because this equation gives us a prediction. So that's often commonly used in stats, is anytime it's a predicted value, we put a hat over it. So just like the little caret thingy. How do we know the line of best fit, the best fit line does the best job? Well, what the algorithm, what the process does internally is that it minimizes what's known as residual error. So what are residuals? Residuals are the difference between model prediction and the actual data values. So a residual, well, let's get an actual pen here. A residual has the equation y minus y hat. Well, what's the difference here? Well, the y is the actual, this is the actual data value. This comes from the data. Okay? And then the y hat is the predicted version. So what we're doing is we're calculating that difference between what the real actually observed value is minus what our predicted model is telling us. Okay? And so these errors are minimized when we have the best fit line. So that's how we're able to choose one specific line. Okay, what are the conditions necessary to calculate a best fit line? Well, we're dealing with, quantitative things, right? We're talking about quantitative variables that we need to have. So we have to have quantitative variables. We can't do a best fit line if you're dealing with categorical variables such as, gender or a student's, status at the school, whether they're a freshman or a sophomore. We need quantitative variables for linear regression. Also, the next 2 points are kind of related. The scatter plot has to be relatively straight. In fact, the stronger the correlation, the better the model prediction will be, right? And we talked about correlation in the previous lecture. It'll show up here again. And kind of related to that is that no outliers, right? That kind of goes hand in hand with the straight scatter plot. We can't have too many outliers. That will just throw off the calculations. It will skew the results and influence our values too much. All right, how to calculate the line of best fit. So here I'm giving you some formulas on how to calculate the slope and the intercept. As you guys know, it's going to be quicker and more efficient for us to do this using technology, whether that's your calculator or Excel or StatCrunch. So we will do it that way, but I wanted to present you with the formulas. So our slope B1 is R. If you recall, R from the previous lecture is the correlation coefficient. And we take R times the standard deviation of the Y values and divide that by the standard deviation of the X values. So that's how you get your slope of your best fit line. Okay. And then our y-intercept is found by taking y bar, which is the mean of the y variable, minus b1, which is our slope, times the x, x bar, which will be the mean of the x values. So those are the formulas that our technology will be doing internally. We're not going to really do this by hand. As I said, we're going to be using some of our aids. All right, and then lastly, before we jump into an example here, is speaking of R, we can actually square R, and it gives us a useful, I guess, kind of interpretation. So R squared, so if you square your correlation coefficient, it gives you a percentage of the variation that is explained by the model. And what I mean by explain is that how good is our model mimicking that variation we see in the data, right? The higher the R squared value, the better our model will be at predictions. And that goes in what we said earlier. We said higher the correlation coefficient, the better our predictions will be. That's because if we square it, we're going to get a higher value. So that's what R squared is. R squared is just used to explain the variation in the data by our model. And so the higher the percentage, the better our model is fitting. So think of R squared as just kind of a way of measuring how good our model is fitting the data. Okay, so yeah, maybe we should write that. So R squared measures how well the best fit line fits or matches the data. Okay, the higher the percentage, the better. All right, here we go. Let's see here. We got an example. It is difficult to determine a person's body fat percentage accurately without immersing them in water. Researchers are hoping to find ways to make good estimates, so they immersed 20 male subjects to measure their waist and recorded their weights. And they calculated their body fat percentage. I don't think that's made clear here, but they calculated their percent body fat as well. The data from these measurements have been loaded into StatCrunch. So part A is they want us to create a scatter plot of body fat versus of percent body fat versus weight. Comment on the trend viewed in the scatter plot. So really quickly, if you guys remember from the previous lecture, we said that when you have a variable versus another variable, they're telling us that they want the first variable to be the y value, and they want the second one to be the x variable. Okay, so y value will be body fat, percent body fat. The x variable will be weight. So let's hop over to StatCrunch and let's create a scatter plot and let's identify if we see any trends. All right, so in StatCrunch, we can see here, this is our data set. The first column is the weight of 20 males in pounds. The second column is their corresponding body fat percentage or percent body fat. Okay, so how do we calculate a scatter plot? That's our first order of business. We know how to do that. We go to graph. When we go to scatter plot somewhere, right here. All right, x variable, it is weight. Y variable, and it's body fat. That's it. Let's go ahead and compute this. And boom, we get a scatter plot. So what can we see here? We certainly notice there is some positive association. Once again, go back to the correlation video if you don't know what that means. So this means that if there's a positive correlation, positive association, linear association, that means that as the weights increase, that's the x-axis, as the weights increase, it appears that, roughly speaking, the percent body fat is also going up. So that is our trend, okay? Let's write that down. So as weight increases, the body fat also increases. Okay? That's what it means to have a positive association. You're moving together in the same direction. As the x value increases, the y value also increases. All right, good. Are the conditions met for a linear regression? So if you recall, the first condition is that we need quantitative variables. Okay? Well, we certainly have that. Weight is quantitative and the percent body fat is quantitative. So those conditions are met. Second condition, and really the third condition also ties into this, is that we need to examine the scatter plot and see if it's straight enough and see if there's any outliers. So is the scatter plot straight enough? Okay, so this is a subjective term, but you know, as we look at it, it's relatively straight. I mean, it's not perfectly straight. No data, no actual real life data will be perfectly straight. But yeah, it's relatively straight, and I think a best fit line will be appropriate here. So is it straight enough? Yes. Are there any outliers? I didn't see anything egregious. Did you? Yeah, there's no outliers in this data set, so we are all set to perform linear regression. All right. Part C, let's calculate the best fit line. All right. So to do that, instead of using the formulas, we're going to let StatCrunch do all the work for us. We go to Stat. We have seen this before. We go to Regression, and we go to Simple Linear. We're doing a simple linear regression. Once again, the x variable is weight. Y variable is body fat. Down here it says perform. We're not really worrying about that. If you're curious, what they're doing here is they're performing a hypothesis test to determine if the intercept and the slope are significantly different than 0. Like I said, we won't have to do that in this course, but that's what they were asking for there. All right, let's go ahead and compute this. And boom, we get a wealth of information, folks. First of all, they tell us what the dependent, which is a fancy way of saying y variable is, and the independent variable is x. So that's good. And then they give us, I like this, they give us the best fit equation right here in terms of the variables. Instead of just y's and x's, they actually tell us what the variables are, right? So, and then these same values, right? Notice that your intercept is down here. It's a negative 26.71, and the slope is a 0.25. So they just grab these numbers and put it into the equation of a line. So let's write that down. So we'll write it down two different ways. So we have y hat equals, it was what was it, negative 26.71 plus 0.25x. Let me double check those. Yeah, that was it. But in terms of the actual variables, if you want to sub in what y and x represent, this is the predicted body fat. So let's put a hat over it. It's the predicted body fat equals a negative 26.71 plus 0.25 times, and the x variable is weight. So that's where, that's why they wrote that at the top of our output there in StatCrunch. They were just substituting in the x and y variable. All right. Interpret what the slope means for this data set. So we have a slope of 0.25. Notice it's multiplying weight. And so what a slope means is that as we increase the x value, in this case weight, by 1 unit, that means that the body fat, the y variable, will go up by whatever the value of the slope is. So since the value of the slope is 0.25, here is the interpretation. An increase of 1 pound. Okay, once again, for your note, so know that that's just our x variable. Okay, so an increase of 1 pound will increase, and it's going to increase because this comes from because the slope is positive. Okay. Anyways, an increase of 1 pound, an increase in 1 unit in the x direction will increase, because the slope is positive, will increase the body fat percentage by, what was the value of our slope? Our slope was a 0.25. So it's going to increase our body fat by 0.25. All right. Excellent. Okay, part E. Calculate R squared and interpret what it means. So, yeah, I thought so. StatCrunch did the work for us, folks. Do you see right here where it says R? So R turns out to be a 0.680. So that's pretty moderately to even maybe a little strong correlation there. And then they already did the R squared for us. That R-SQ is R squared. It's 0.462. So let me write that down. So R was a 0.680. Remember, R goes between -1 and +1. And R squared was a 0.462. So quickly, let me show you, in case for some reason you don't have that output there. If I take a 0.680 and I square it, there's that 0.462. So that's all they did. They just took the R coefficient, which we talked about in the previous lecture, and they squared it. All right. And what does that mean? So remember, R squared is a percent explains the percent variation in the model, right? So this means that our model explains or accounts for 46.2% of the variation in the data. Okay, so that's the interpretation. Just basically means that, you know, there's natural variability in this data. I mean, it's just going to be all over the place. But our model is doing a job of tracking about 46.2% of that variability that we're seeing. Okay? All right, so your R squared is a percent. So write it as a percent. All right. Next, predict the percent body fat for a person that weighs 200 pounds. So what I want to do here is, first I want to rewrite my equation. So my equation was y hat equals a negative 26.71 plus 0.25x, where remember x is equal to the weight and y is the percent body fat. All right, so to predict the percent body fat, all we have to do, folks, is plug in 200 for x. Straightforward, easy peasy. So the predicted body fat will be a negative 26.71 plus 0.25 times the weight of this individual, which is 200 pounds. Let's work that out to get, let's see, negative 26.71 plus 0.25 times 200 pounds. We get a percent body fat of 23.29. Okay, that is our prediction. All right, last part here. What is the residual error for a person that weighs 185 pounds and has 6% body fat? So early in the lecture, we said that the residual in error is the predicted value minus the actual value. So predicted minus actual. All right. So what we're going to have to do for this question is, first of all, we're going to have to calculate our predicted value. And then we're going to compare it to the 6% that this person actually has. Okay. All right, so let's do that. So once again, the same thing we just did in the previous part. Y hat is a negative 26.71 plus 0.25 times x, or x's weight. So the predicted value is a negative 26.71 plus 0.25 times the person's weight is 185 pounds. Let's calculate that. Negative 26.71 plus 0.25 times 185. We get a answer of 19.54. 19.54. All right. So now what's the residual? The residual would be our predicted body fat for that person of 19.54 minus their actual body fat of 6. And we don't need a calculator for that. We get a difference of 13.54. So the model predicted the person's body weight to be 13.54 more than the actual body fat. Okay, and I'm sorry, this shouldn't be weight up here. This should be body fat. Okay, does that make sense? So we did y hat minus y. We got a difference of a positive 13.54. That means that the model, the best fit line, is predicting a value a little higher than what actually happened in reality. But once again, if we had a better fitting data set, we would come closer to that person's 6% body fat. All right, guys, that will wrap it up for this video. As always, I appreciate you guys, and I look forward to seeing you in some future videos. You guys have a great one.